In this video, we'll be taking a closer look at colligative property calculations. Colligative properties are properties of solutions that differ from those of a pure solvent, and they depend on the concentration of the solute rather than the type of the solute. Boiling point elevation and freezing point depression are two types of colligative properties that we will investigate in this video. As an example, the pure solvent water has a boiling point of 100 degrees Celsius. But when a solute is dissolved into water, the boiling point of that solution will be higher than 100 degrees. That is due to the presence of the solute particles in the solution and how they interact with the solvent particles. This is the equation for doing colligative property calculations involving boiling point elevation for a solution. The delta T sub B stands for the change in the temperature. The subscript B tells you that we're referring to boiling point elevation, the number of degrees to which the boiling point is elevated. The I is the Van Hoff factor, and it stands for the number of solute particles per mole of the substance that is being dissolved, the solute. For example, in sodium chloride, there are 2 ions that will be produced from the dissociation of 1 mole of sodium chloride. And colligative properties are based on the number of particles, not necessarily the type. So we have to have the Van Hoff factor present to account for those solutes that dissociate into ions or multiple particles. The K sub B stands for the molar boiling point constant. This value is solvent dependent. In other words, it changes depending upon the solvent that you're using. And the lowercase m stands for the molality of the solution. Molality is moles of solute divided by kilograms of solvent. Here's a practice problem involving boiling point elevation. If 45 grams of sodium chloride are added to 500 grams of water, what will be the boiling point of the solution? The molar boiling point elevation constant of water is 0.512 degrees Celsius per mole. Remember, our equation has a few variables. The delta T sub B is the change in temperature, in this case the boiling point elevation. I is the Van Hoff factor, K sub B is the molar boiling point constant for water, and m is molality. Let's take the I first, the Van Hoff factor. We're dealing with sodium chloride, which is NaCl, and when sodium chloride dissolves into the solution, it will produce 2 ions, Na+ and Cl-. So, assuming ideal solution behavior, which we will do for simplicity in this video, the Van Hoff factor for this solution will be 2, the 2 moles of ions per mole of sodium chloride. The molar boiling point elevation constant for water is 0.512, so we'll place that here. The molality for the solution can be found by taking the moles of the solute that's dissolved divided by the kilograms of solvent. So we need to convert 45 grams of sodium chloride to moles of sodium chloride. And we do that by setting up a conversion chart, and we put 45 grams of sodium chloride in the upper left-hand corner, and bring down the units of grams of sodium chloride to the denominator, and use the molar mass of 58.44 to convert to moles of sodium chloride. We can cancel our units for grams of sodium chloride, and when we multiply 45 times 1 divided by 58.44, we find that we have 0.77 moles of sodium chloride. For molality, we need to divide the moles of solute by the kilograms of the solvent, which is the water. We take the 0.77 moles of the sodium chloride and put that over kilograms of solvent. 500 grams of water was given to us in the problem. And if we convert that to kilograms by moving the decimal 3 places to the left, we have 0.500 kilograms. And so when we take the 0.77 and divide it by 0.500, we find the molality of this solution is 1.5. We bring the 1.5 up here to our equation and we plug it in for molality. And we have a Van Hoff factor of 2, which comes from the sodium chloride, which broke up into 2 ions per mole. And when we multiply 2 times 0.512 times 1.5, we get the number of degrees to which the boiling point is elevated. And that answer is 1.5. But we have to be careful here because the question asks what will be the boiling point of the solution, not the degrees of elevation. This number here, 1.5, only represents how much the boiling point has been elevated, or in other words, the change in the boiling point. So take the normal boiling point of water, which is 100 degrees Celsius, and add the 1.5 degrees that we just calculated. And we find that the boiling point of the solution will be 101.5 degrees Celsius, because it has been elevated 1.5 degrees due to the presence of the sodium chloride. Freezing point depression is another type of colligative property. Just like the boiling point elevation, the presence of the solute is going to change the property of the solution relative to the solvent alone. For example, water, just pure solvent water, freezes at 0 degrees Celsius. But if we add a solute to it and dissolve it in the water, the freezing point will be lowered or depressed. The equation for this is almost identical to the previous one. However, the subscripts are different because we're dealing with freezing point depression. So delta T sub F represents the decrease in degrees of the freezing point. I still stands for the Van Hoff factor, K sub F is the molar freezing point constant, and M is the molality of the solution. Here's a practice question that asks us to calculate the freezing point depression of a sugar solution. If 5 grams of sucrose is added to 145 grams of water, what will the freezing point of the sugar solution be? The molar freezing point depression constant for water is 1.858 degrees Celsius per mole. So let's look at the equation. I stands for the Van Hoff factor, as before. However, in this problem, sucrose is the solute. Sucrose is considered a non-electrolyte. So when it dissolves, it's not going to break apart into ions, so our Van Hoff factor is just going to be 1. In other words, for every mole of sucrose that dissolves, we will get 1 mole of solute particles. That will make this calculation simpler than the previous one. The molar freezing point depression constant of water is given to us, 1.858. And now we need to figure out the molality of the solution. And molality, again, is moles of solute divided by kilograms of solvent. To get the calculation started, take what's given, the 5 grams of sucrose, which is C12H22O11, and place that in the upper left-hand corner of a conversion chart. Bring down the units, the grams of sucrose, and convert from grams of sucrose to moles of sucrose. The units of grams of sucrose cancel, and when we take 5 times 1 divided by 342.30, we find that the number of moles of sucrose, if we have 5 grams, is 0.015. To calculate molality, take the moles that we have, the 0.015, and divide that by the kilograms of solvent. The question tells us that we have 145 grams, but we need that in kilograms. So move the decimal 3 places to the left, and we get 0.145 kilograms of the solvent, water. When we divide 0.015 by 0.145, we find that the molality of our solution is 0.10 mole sucrose. We plug that number in for the molality in the equation. Now we plug 1 for the Van Hoff factor, for I, and we plug in the 1.858 for the molar freezing point depression constant for water. Then we plug in the 0.10 for the molality, which we just calculated. And when we multiply these 3 values together, 0.19 degrees Celsius is going to be the delta T sub F, or in other words, it's going to be the change in the freezing point, which is going to be depressed or lowered. If we want to know what the new freezing point of the sugar solution will be, we take the original freezing point of the solvent alone, which is 0 degrees Celsius, and we subtract the 0.19 from that. And what we have is the new freezing point of this solution, negative 0.19 degrees Celsius, and that's due to the presence of the sucrose that's been added to the solution. Now here's one for you to try. If 22 grams of sodium chloride are added to 700 grams of water, what would be the new freezing point of the solution? The molar freezing point depression constant for water is 1.858 degrees Celsius per mole. When you're ready, press pause, give it a try, and then come back here and press play to check your work. Did you get -2 degrees Celsius as the new freezing point of the solution? If you did, good work. If not, let's take a look at how we got there. Since we're discussing freezing point depression, we use this equation, in which the change in the freezing point can be found from the Van Hoff factor times the molar freezing point depression constant times the molality. There's a 2 here because we have a strong electrolyte, sodium chloride. So for every mole of sodium chloride that is dissolved, we're going to get 2 moles of ions. The constant was given to us, and we plug that in for K sub F. We determined the molality by taking the 22 grams of sodium chloride that was given to us, using the molar mass from the periodic table to convert to moles of sodium chloride, and then we took the moles of sodium chloride and divided it by the mass of the solvent. But it has to be in kilograms because molality is moles of solute divided by kilograms of solvent. So we took the 0.38 moles and divided that by the 0.700 kilograms, and we found that the molality of this solution was 0.54 mole. That value is plugged into the equation for M. And then when we multiply 0.54 times 1.858 times 2, we get 2.0. And that is the change in the temperature for the freezing point depression. Then we take the original freezing point of the solvent alone, water, which is 0 degrees Celsius, and we subtract our delta T, the 2.0, and this is the new freezing point for the solution. Again, it has been lowered or depressed based on the presence of this solute that's in the solution. And that's a closer look at colligative properties. If you'd like more chemistry matters, go to the home page where the entire series is available to you.